Hey everybody, and welcome to Chapter 6. So Chapter 6 is all about sampling distributions. Normally on this first slide I try to tell you a little bit about this chapter, but this is one of the more abstract chapters. I don't think that it's particularly hard in terms of calculations. You're actually going to find there's not a whole lot to calculate here. We're really going to focus on calculating one thing that's new at least, and that's called the standard error of the mean. But for the most part, think of this as like a continuation of the last two chapters. Chapter 4, we learned about z-scores and what z-scores are. Remember that z-scores are a measurement of distance away from the mean. The chapter after that, Chapter 5, we talked about probabilities. So what is the likelihood of picking one of those values in a distribution? What is the likelihood that that value has given the spread, right? And we talked about, finding a z calculator and things like that to do that. Now we're going to be kind of expanding on that. And so this is a little bit abstract. This is more of a theory-based chapter, in my opinion, where we're going to be talking a lot about statistical theory and less of the application side of things. But that's all okay, because this is all going to feed into the second half of our class, or the second half of our course this semester when we start talking about hypothesis testing. It all comes from this idea of sampling distributions, so let's get into it. This is probably going to be just one long video, just like Chapter 5 was. It doesn't really have a clean break like some of the upcoming chapters do. So we're going to be revisiting this idea of samples versus populations, the way that they're different. We're going to be talking about what happens whenever you have multiple means. So if you were to go along and do multiple samples of the same population, how do you figure out what the correct mean is? We'll talk about the central limit theorem and the law of large numbers, some kind of theoretical, aspects of our class, and we'll talk about what standard error is and why it's important. There's a good chance you have seen it on the news and may have not known what it was. So let's talk a little bit about samples and sampling. So remember that when we talk about sampling, what does sampling mean? Sampling means that we have a population that's filled with lots of potential observations, potential people we could be asking, or we could be interviewing, or we could be researching. It's unfeasible to do the entire population, so instead we're going to do a sample. So whenever we do a sampling, basically what we're saying is that we're going to take a sample, and maybe we take another sample, and maybe we take another sample, and another sample. If we're dealing with something like, for example, the state of Massachusetts, getting a sample of 30 people is not so helpful, right? Instead, we might, because this is one of the things we talked about in chapter 1. Instead, we might want to go through and sample some people from Western Mass, some people from Central Mass, some people from Northern Mass, some people from Southern Mass, and so on. That when we do that, we are sampling multiple distributions now. So a sampling distribution, what that is a distribution of stats that would be created if we were randomly sampling from the same population. So this sampling distribution is a theoretic distribution. It's not an actual distribution, but it's essentially what happens whenever you have multiple samples, how they create their own distribution that should reflect the same characteristics of the population. Okay. I'm already getting very abstract, I feel like. So to put it another way, is let's say that this is the actual, I'm going to use IQ later, so I'm not going to use that as an example here, but I could say that this is, for Massachusetts, this is height. So this is the average height in Massachusetts. But again, I can't measure every single person in Massachusetts, so I'm going to go about and I'm going to sample 30 people from each big city in Massachusetts. And what that gives me is now I'm going to have one sample that looks like this, one sample that looks like this, one sample that looks like this, and one sample that looks like this, and so on. We're going to have a lot of different samples, a lot of different distributions. The sampling distribution then is going to be, for this, it would look something kind of like this, where we have now a distribution created from sampling. So it's not exactly the same thing as a population, but it's a representation of that population. So it's possible basically that the more we sample, the closer it's going to get to this population distribution. But there's always the likelihood that whenever we choose some of these samples, that they're not going to be completely representative of the whole. So sampling distributions are going to be used to calculate the probability that samples that we get come from chance. So for example, we're dealing with this right here. Let's say that we measure somebody from I don't know, North Adams, and we find their distribution is actually something like this. So this one sample right here looks to be very, very different than these others. And if we know that it looks like this sample doesn't really belong, then we can start to say, wait a second, it looks like maybe the people from North Adams are not the average height of Massachusetts. Maybe they are part of a separate population. That maybe there's something in the drinking water that's causing them to be taller, or whatever. And that's all important because in later chapters, when we start doing hypothesis testing, when we start looking at whether or not two groups are the same, or if two groups are different, this is what we're going to be relying on, this idea of a sampling distribution. All right, so let's go through an example here. And this is, depending on the context, there's always political races going on, right? And so every time I teach stats, I get kind of excited whenever there's midterms or whenever there's an election coming up, because, at least for me, as a little bit of a numbers geek, I like to pay attention to these polls, and I like to see where candidates are, how they're doing, what the race looks like. So let's say that a political candidate gets support from 47% of the voters in their jurisdiction. That's going to be from 100 voters. So obviously, it's not feasible to, let's say that we're just talking about Westfield here. So if we're talking about the mayor of Westfield, it would be unreasonable for us to ask every single person in Westfield who they're going to vote for. So instead, we're going to call up 100 likely voters and we're going to ask them directly, who are you voting for? And when we do that, out of that 100, 47 of them said they are going to vote for candidate A for mayor. And so if that's the case, then inferential stats is going to tell us that if we were to exaggerate that to the population of Westfield, we can probably expect about 47% of the population to adhere to this, because we just got a sample, we found that to be the characteristics of the sample. We're going to assume that it is an accurate representation of the population, and if that's true, then this candidate is in trouble because they are below 50%. They're probably not going to win. But as I'm going through this example, you can probably already smell where this is going, because I'm talking about 100 voters. How do I know that those 100 voters are accurate representatives for people that are actually going to vote? We see this a lot, especially in recent, especially presidential elections, where a lot of the polls seem to be skewed in one direction or the other, and then when it comes time to actually vote, the polls seem to be incorrect. Why are they incorrect? Well, there's lots of reasons for that, and you could probably identify some based on what you learned in Research Methods 1, but usually it's that whoever the sample is may not be an accurate representation of who actually shows up to vote. So inferential stats is going to tell us that 47% of our population is going to vote for candidate A. But, and this is the thing that you may have seen on the news, is the margin of error. So what does it mean to have a margin of error of plus or minus 4? Because that's an expression I see quite a bit. What does that mean? Basically, it means that the true number of support of the population of the entire city of Westfield is going to be about 47%, but we know that that's not going to be a rock-solid number, a rock-solid estimate, because 100 voters is kind of a small number whenever you think about how many people are in Westfield. And so we're not guaranteeing that it's going to be 47%. We think it's going to be in the ballpark. So we're going to cut ourselves some slack, and we're going to say that it's going to be 47 plus or minus 4%, which means that the actual population is going to vote somewhere between 43% and 51% for candidate A. So even though this doesn't look super good for candidate A, because they have 47% and that's not the majority, this 4% plus or minus means that they could actually score as high as 51%, or they may score as low as 43% when we actually measure the people who vote on election day. Where do these numbers come from? Because it is 47 minus 4 and plus 4. And that's going to give me 51 and 43. So that's where that comes from. So this chapter is all about how do we measure margin of error? Where does that estimate come from? So margin of error is going to come from the sampling distribution, and we're going to use the margin of error as basically like a 95% cutoff here. And so 95% is going to refer to the possible sample means that we could be getting. So we are assuming that this number 47 is just an estimate. That is not the actual representation of who's going to be voting for candidate A, but is an estimate based on the numbers that we get. Which means that out of that, if we extrapolate to other samples we might collect, that should fit with 95% certainty somewhere between 43% and 51%. In other words, we're 95% confident that the population is going to vote somewhere between 43% and 51% for candidate A. Why do I say 95%? Because if you think back to chapter 5, remember the z-scores and how we talked about how we know where these values are coming from based on their z-scores and how far away they are from the mean? That's exactly what we're going to do. We're going to look at in 95%, so roughly, not totally, but roughly 2 standard deviations above and below the mean for the sample. So let me give you a more concrete example here. So we're going to test IQ scores because I like using IQ as an example because it always gives you a mean of 100. You know that's the population mean, and you know that the population standard deviation is supposed to be 15. So we got a lot of things that we already know, and these are nice round numbers. 100 is a nice number to subtract from others when we're doing, when we're trying to calculate standard deviation or z-scores. So IQ is just a nice practice for us. So we already know the population characteristics here. So let's say that we start sampling now. So I'm going to go through each individual town, and I'm going to sample 100 people and then see where their IQs are. So let's say that I go to Westfield and I pick 100 people and I find that the mean there is going to be 110. So the mean IQ in Westfield is 110. And then I try, let's say, South Hadley, and it's 105. And then I try, who is Westfield's rivals? I don't know. Is it, I don't know. I was trying to start some trouble here. Let's just say that this is, I can't think of a town that none of you live in. So let's say that this is, I'm going to say Natic. I'm going to say that's Natick. And it's just because I don't know how to actually pronounce Natick. I know some of you may be from there, and I'm sorry. But let's say that out of 100 that I chose there, that the mean was about 60. And then this other town, it was 90. And then this other town, it was, closer to 100. This one's closer to 130. And I keep adding them up. So I'm adding up all of these. And so you can see what's going on here, that a lot of the sample that I'm choosing, out of all these different towns, all these different samples, that they're starting to represent or starting to look like a nice normal distribution. And that's true. Basically, the more sampling we do, the closer this distribution is going to look like the actual distribution of the population or of the standard normal distribution. So if we decided to look at this in terms of z-scores, then you can kind of see where I'm going here, that I'm going to have my cutoffs right around here for 95%, and basically I would say that, what's the likelihood of reaching into a random town and having an IQ between 70 and 130 is going to be 95%, which means that roughly 2.5% likelihood to choose a town at random and they be below, or 2.5% likely that I choose a town at random and they are, just by chance, above that population. Above 130. Where did 2.5 comes from? Because I said 5% overall, right? Because this is 95% likely to be falling in between these two posts. So 5% is going to be allocated on each side. That's where the 2.5 comes from. All right, sorry about that. All right, there we go. So this means that the sample means are going to stack up into a normal curve, and we call that the sampling distribution. So remember, the sampling distribution is a distribution of multiple samples. So it's a little bit different than a normal distribution. The normal distribution, as you may remember, is supposed to represent a population. Alright, so we can make predictions based on this. So the shape of the distribution is going to tell us how likely or how precisely we are representing the population. So were our chances good that we're going to choose, at random, what's the likely, how likely is it that we're going to choose a sample mean that is 30 points away from 100? Turns out it's not going to be super likely, right? It's going to be, not so good. But if we're talking about what is the likelihood that we're going to choose a town at random that is exactly 100, if we go back, it seems like it's actually going to be pretty good, right? Because we got a lot of those stacked up right here in the middle. So choosing a town at random and them actually representing the population is actually kind of likely, But still, there's so much random variability that it's hard to be 100% certain of that. So because this curve is very wide, it's kind of likely that if we just sampled one of them, they're not going to be exactly at 100. So that's why it helps to sample multiple times to try to find that sweet spot for the population of where that population mean actually is. So again, just to go back, assume that we don't know the population IQ. If we just studied one, this would give us an incorrect assumption about where the population mean is. If we did just this one and got the average between those two, again, it would not be a fair, accurate representation. If we just did this one, again, it would not be accurate. But if we did a lot of those, now it's starting to look more like the population. In other words, the more we sample, the better. That is a big rule for Chapter 6. The more we sample these, the more accurate our estimates are going to be. So if we can determine the variability here, then that's going to tell us how close we are to finding that population's mean. So finding the spread of that distribution is important. Why is it important? Because of this. Here what we're looking at, this has a very low standard deviation, which means that there's not a lot of variability in our data. This has a very high standard deviation, which means that there is a lot of variability in our data. So, in other words, we could be really confident if our sampling distribution looks like this, because it means there's not a lot of variability in our samplings. If our sampling distribution looks more like this, though, then we're kind of in trouble, because it looks like there's a lot of variability here, and we can't really be super certain about the population because there's so much variability. This brings us to the central limit theorem. The central limit theorem asserts, and I'm just going to read this word for word because this is straight from the textbook that we use, and then we can talk about what it means, because even though it's a direct quote, it doesn't really I'm trying to think of how to put this. It doesn't make for light reading. It's not something that you would want to read in an airport. So for samples of a single size of n, remember that this is representing our sample size, drawn from a population with a given mean u, so that's our population mean and a variance of sigma squared, the sampling distribution of sample means will have a mean of mu x bar equals mu and variance x equals variance divided by n. This distribution will approach normality as n increases. There's so much to break down here. What the hell does this actually mean? Basically what we're saying here is that for samples where you have a single size of n drawn from the population, that the more we sample, the closer it gets to normality. So as we increase the sample, we're getting closer and closer and closer to a distribution that looks like this. It looks like our normal distribution. So that's one part of it. The other part of it is saying that the sampling distribution, that the samples that we get, that the sampling distribution, so that distribution that's created from samples, is going to mirror the population's characteristics, such that the population mu, which is what we're seeing right here, is going to be equal to the population mean of all of the sample means. Okay, What the hell does that mean? Basically, it means that if we go back to this example, where we have so many different samples here, that if I got the mean of all of these samples, that mean would be the population mean. That's what it's saying. So if we get a lot of samples, then the mean of all of those samples should be pretty close to our population. And the standard, the variance of that distribution should be pretty close to the standard deviation of that distribution. All right. So so sampling from the means of the distribution will create a normal distribution, and the normal distribution will take on the same characteristics. And when I say characteristics, I just mean the mean and standard deviation of the population as you increase that sample size. So if we're looking for the average variance has a name, and that average variance is called the standard error of the mean. There's not real, we don't, when we're talking about population means or sampling means, we don't really have a good way of talking about that. We don't have a word for that. We would just usually say, like the sampling mean. But the standard deviation or the variance of the sampling distribution is referred to as the standard error of the mean. And you can think of that as kind of like it is the average or the most common standard deviation of all of your samples that you have collected. So in order to do that, the way that we're going to calculate this is that we're going to get our standard deviation of the mean, and then we are going to divide that by the square root of n. So we're going to collect our standard deviation, and then we are going to divide that by the square root of n, where n is going to represent how many samples we have. This is and this is why you may remember at the very beginning of the semester, I was like, be careful, because capital N and lowercase n mean different things. So here's why this is important. Because for standard deviation, you're going to calculate that as you always have, where capital N refers to how many values you have in your data set. No big deal, no sweat, you've already mastered this, you're good at it. Here, for standard error of the mean, we're going to be dividing what we get here, the standard deviation, by the square root of the total number of samples we have. So this is our total number of samples. And essentially, the larger this value is, the smaller the standard error is. The fewer samples you have, the larger that standard error is. So, without going into too much detail about the analysis, if this was if we only had one sample, our standard error would be equivalent to our standard deviation. Why? Because this would be 1, the square root of 1 is 1, 1 over the standard deviation is just going to be the standard deviation, so our standard error would be equal to our standard deviation. And that's not really helpful. That doesn't really make a whole lot of sense to do it that way. You would just report the standard deviation. So the standard error, again, think of that as a way to try to approximate and estimate where the actual average standard deviation is whenever you account for how many times you have sampled from that population. So you may remember that I showed you a figure that looked a little bit like this back in Chapter 3 when we were talking about dispersion. What we're looking at here now is essentially going to be the same idea. That here we have an N of an N of 10, so it's capital N, which means that this is how many participants we have. So blue, we have a lot of variability here. It's a very wide distribution because we have a very few number of people. Yellow is the tallest and the most narrow, so we're going to have the most accurate predictions here in yellow because we have more people here. This is called the law of large numbers. The law of large numbers is simply that the larger the sample you take is, the closer that sample's mean is going to be to the population's mean. So it's a little bit different from central limit theorem, because central limit theorem is saying that you have to do this with multiple samples. Law of large numbers is saying that, hey, the larger your sample is, the more accurate you're going to be in your estimates of the population. So the number of repetitions of the experiment is increased, the relative frequency obtained in the experiment tends to become closer and closer to the theoretical probability. That's just a very fancy way of saying what you see here. The larger samples you take, the closer you get to the mean of the population. Alright, so here we're looking at the standard error, and this is just to show that with the sample size, the larger you increase your sample size, the more the smaller your standard deviation generally gets. Here we're looking at standard error because remember we're looking at the average standard deviation, but essentially the larger that sample gets, the smaller the standard error gets. The lower the sample size gets, the larger that standard error gets. So if you are a researcher, it behooves you to collect larger samples compared to smaller ones because they're going to give you more accurate estimates for your work here. So calculating so we can use all of this that we've done so far and apply it to Chapter 5 and earlier. So we're going to start calculating z-scores from this and then just look them up like we did in the last chapter. We're going to plug them into a calculator and try to find the probabilities of where these samples come from. So calculating probabilities from a sampling distribution is going to be the exact same of what we did in Chapter 5, where we're going to be using a sampling distribution, but we're going to treat it like a distribution because that's what it is. The only difference here is that instead of using the standard deviation, we're going to be using the standard error. Because the standard error, that's going to be our go-to measurement of variance or of dispersion when you're using a sampling distribution. When you're just using a sample or when you're using your population, it's totally okay to use standard deviation, but we're not going to do that here this time because we are looking at a sampling distribution. This is going to give us a more precise and more conservative estimate compared to using standard deviation because standard error is going to be a smaller estimate compared to standard deviation. So the steps that we're going to do here is we're going to find the z-score. So we're going to compare our sample mean to our population mean. So how is this different than what we've been doing? Before, you may remember that we used a formula that looked like this. Z is going to be equal to x minus, depending on what you're using, it could be either mu or x bar divided by sigma, right? Now it's going to be a little bit different. We're going to be changing this up so that it's going to be something more like this. X bar minus mu divided by the standard error of the mean. And that's sigma with the x bar is standard error of the mean. So what does this mean? How do we interpret this? Z is going to be equal to the sampling mean subtracted by the population mean divided by the standard error of the mean. That gives you your z-score for your new sample. So we're going to calculate the z-score for our sample. We're going to look up that z-score in our z-table or the calculator that I showed you previously, and then that is going to be everything to the left of that number. So let's go through an example. All right, so our example here, let's say that I'm interested in looking at attention as it varies across Westfield State University. And I'm going to do this by giving students an attention test. As a cognitive psychologist, this is totally something that would be up my alley. I'd be very interested to do this. And I'm going to do this class by class. So you can think of it that way, that each class is going to be its own individual sample. But I want to generalize to the rest of the university. So the question then is, how many, or how many classes do I need to sample in order to get a good estimate for the population of the university? Now let's say that I know that the university's mean, in other words, the population that I'm looking at, that the mean for the population is 50, with a standard deviation of 10. So if I were to go and grab 10 separate classes and do this attentional test, and I got 10 separate sample means, there's a chance that those sample means could be right there around the population mean, but there's also the expectation that there's going to be some variability here. My 8:15 class is probably going to have really high attentional scores. My 3 o'clock class is probably going to have lower attentional scores. So what is the likelihood then, and this is something you could probably expect on your quizzes and on the exam, questions like this, what is the likelihood that those 10 class means are going to fall between 47 and 53? So, how do I calculate this? Let's think about what we're asking here. I'm asking, and again, I love drawing out these sampling distributions to help visualize what I mean here. So let's say that we know that the population is 50 and it has a curve that looks like this. So I get 10 class means. What is likelihood they are going to fall somewhere between 47 and 53? So here I have a standard deviation of 10. So I could probably expect, you know, something that looks kind of like this. We're going to find this is maybe not totally accurate to scale. And so what is likelihood that somebody is going to be, you know, basically between this section right here, between 47 and 53, if I were to choose 10 class means? And then what would be that same probability if I were to get 50? So why, I mean, wouldn't it be the same thing? It wouldn't. And the reason why, if you think back to earlier, we're going to find that depending on how many samples I got, that curve could look like this, or it could look something more like this. And if that's the case, then finding 47 and 53, the likelihoods are going to be very, very different between these two curves. So let's take a look. How do we solve this? Basically, and hey, that's not a bad representation of what I drew, right? I feel I'm not ashamed of myself, not ashamed of that estimate that I made. So if I want to find the z-scores for both 47 and 53, and I'm going to subtract that together to find the proportion that's going to be left in the middle. So for 10, that's going to be 65.78%, and for 50, that's going to be 96.7%. So how did I get those numbers? Let me show you how, using our z-score calculator. Okay, so to solve, if we wanted to solve this, this is how we do it. And it may, and you know, if you want to, you can pause the video and try to backtrack because you know what the answers are. See if you can find it if you want to, but if you don't feel confident enough in yourself right now, that's okay. I can show you how to do this. It takes takes a couple of steps to do, but it's certainly not harder than anything you've learned so far this semester. So the first thing we want to do, remember, is to calculate the z-score. So we want to find the z-score of what? Of 47 and 53. So we can do that using the parameters that we have here. So we want to find the z-score of 47, and so we're going to subtract from that the population. It's going to be 50, and then we're going to divide that by the standard error of the mean. And so actually let me back up for a second here, so I can write out the formula here. So it's going to look something kind of like this. So I'm going to input my estimate here, which is going to be 47, and I'm going to subtract from that the population mean, and I'm going to divide that by the standard error of the mean. So let's go. Let's try this out. So I'm going to plug in 47 here, subtract from that 50, divide by, standard error of the mean. How do I calculate that? So we got our standard deviation, which is 10. So I'm going to write that in here, and remember that 10 is then going to be divided by the samples, the square root of the sample size, or how many samples we got. So here in this question, I had 10 class means, which means I had 10 separate samples, so it's going to be divided by the square root of 10. So whenever I do that, that's going to give me -3 in my numerator, and then this is going to give me, I need to break out my calculator for this, 10 divided by, actually let me get the square root of 10 first, that's going to be 3.16 divided by 10. And so this should look like -3 divided by all of that. So the denominator, I'm doing 10 divided by 3.16 is going to give me, wait, what? 3.16. Okay, I trust it. It just looks confusing to divide 10 by 3.16 and also get 3.16, but that is what you get. And so whenever I have this, 3 over 3.16, so 3 divided by 3.16 is going to give me -0.95. It's actually 949, but I'm going to round that up to 95. So that's negative 0.95. And I'm going to do the same thing for 53, but you'll see that if I do that, I'm going to do the same thing here. So I'm going to do 53 subtracted by 50 divided by all that, and that's going to give me positive 3 divided by 10, divided by the square root of 10. We already know what that is. So it's just going to be positive 3 divided by 3.16, which is going to be positive 0.95. All right, so those are our two z-scores. Now here's where the magic happens, and we were careful because we used the standard error instead of the standard deviation, which is the trick here. So 0.95. So I'm switching over to my z-score calculator. If you want to, there's multiple ways you can find that using this. If you wanted to, you could cleverly put it in here. I'm just going to go down here to probability between two z-scores. That's a really easy way to do it. So I'm going to plug in negative 0.95 and then regular 0.95 here, and I'm going to hit calculate, and that gives me 0.657, and it even shows you roughly what part of the distribution that should be covering. And just to check, yep, that is what we got there, that about 65%, right? So 0.65, the probability is 0.65, which is 65.78%. So, in other words, if we're trying to interpret what we have here, if we're trying to interpret what is the likelihood that of those 10 class means, that if I aggregated them together, got the mean, where would they fall? There's a really good chance, basically 2 out of 3 times, that the average that I calculated here is going to fall between these two goalposts. So if we want to do the same thing for 50 class means, honestly, what I would do if I were in your shoes, I've already written this out. You don't have to change very much to do this. All we have to do is change this piece right here. We have to change the standard error now. So I'm going to be changing all of this. And so that's going to give me, so now the square root of 50, so it should be 7 point something. That's going to be 7.07. And so that's going to give me 10 divided by 7.07, which gives me 1.4. And then, what is this? So it's going to be negative 3 divided by 1.4. It's going to give me 2.14. Is that right? Yes. Okay. Yes, just making sure. And then, the same thing's going to happen down here. It's going to be negative 2.14. If you don't believe me, then we can solve this, just like we did over here. And it's just going to be plus, and it's going to be minus. All right, so we got those values. We can plug that into our calculator now. So negative 2.14 and positive 2.14. Let's see what happens. Negative 2.14, positive 2.14. That gives me 0.96765. And if I pop back over here, that is exactly what I found. So you may say, wait a second, these are the exact same numbers. Why are these z-scores different? The reason why they are different is because the shape of the distribution changes depending on how many samples you acquire. Here, because we've acquired more samples, we're having this really kind of skinny curve. So these z-scores of 47 and 53 are now actually further away from the mean because there's less variability when we have 50 samples. So in other words, increasing the sample size increases our confidence as well. So so we just proved the law of large numbers, and we proved the central limit theorem. So some final thoughts and rules here before we close out this chapter. When we're taking a random sample from any kind of size that has a mean of mu and a standard deviation of sigma, the sampling distribution is also going to have those things as well. But the mean is going to be mu, and the standard error is going to be equal to sigma divided by the square root of n, which we just did. The central limit theorem says that for random sampling, as the sample size grows, the sampling distribution approaches a normal distribution. That probably makes sense, right? And that sampling distributions will be normal no matter what, as long as the population basically, if you sample more than 30 times, you're going to get the population's distribution shape. That's a good way of finding that, and then that's also part of the central limit theorem. This part right here is about large numbers law of large numbers, which is that if your samples are less than 30, the sampling distribution is only going to be normal if your population distribution is normal. And as n increases, the standard error is going to get smaller. So the standard error, in other words, our variability, is going to get smaller because our confidence is going to increase. And as always, as your sample size increases, your precision for these estimates are going to get better as well. And that is it. I'm going to record one more video that's going to basically be a practice problem like I normally do. So catch me in that, and otherwise we're done with this chapter. So thank you so much for tuning in. I will catch you later. Bye.